Hello, and welcome to the Sleepy Astronomer. Tonight, we're drifting back through the corridors of time to explore the life and revolutionary discoveries of Galileo Galilei, the man whose simple telescope opened humanity's eyes to the true nature of the cosmos. From his curious youth in Renaissance Italy to the moment he first turned his lens toward the heavens, we'll discover how one man's persistence in asking questions transformed our understanding of Earth's place in the universe. We'll explore the gentle courage it took to challenge centuries of accepted wisdom, the wonder of seeing Jupiter's moons for the first time, and how Galileo's discoveries continue to inspire every astronomer who points an instrument toward the star-filled darkness above. If you're discovering these tranquil astronomical journeys for the first time, welcome to our quiet corner of the cosmos. And if you've travelled with me before through previous explorations among the stars, it's wonderful to have you back for another peaceful voyage through space and time. Tonight we'll begin in the hills of Tuscany in the late 1500s, with a young man whose restless mind refused to accept that the world was exactly as it appeared. We'll follow Galileo's journey from his early experiments with falling objects to the revolutionary moment when he first glimpsed the moons of Jupiter dancing in their eternal orbit. We'll discover not just the incredible scientific breakthroughs that earned him the title Father of Modern Astronomy, but the deeply human story of curiosity, courage, and the price one man paid for daring to see the universe as it truly is. We'll explore how a simple arrangement of lenses, a telescope barely more powerful than a pair of modern binoculars, revealed secrets that had been hidden since the dawn of time. We'll witness through Galileo's eyes the rough, mountainous surface of the moon, the phases of Venus that proved the planets orbit the Sun, and those 4 tiny points of light circling Jupiter that showed our Earth was not the centre of all celestial motion. So find your most comfortable position, whether you're settled beneath soft blankets, resting peacefully on the sofa, or perhaps lying back where you can glimpse through your window the same moon and planets that Galileo studied 4 centuries ago. Take a slow, deep breath, and let's begin our gentle drift back through time to meet the man whose careful observations and revolutionary insights opened the door to our modern understanding of the cosmos. Galileo Galilei, the curious soul who taught humanity to truly see the heavens. Picture, if you will, the rolling hills of Tuscany in the year 1564, where olive groves shimmer silver-green in the Mediterranean sunlight, and ancient stone walls trace lazy boundaries across a landscape that has barely changed since Roman times. The air carries the scent of wild herbs and cypress trees, and in the distance the towers and red-tiled roofs of Florence rise like a dream against the soft blue sky. Into this world of Renaissance wonder was born a child who would grow up to fundamentally change how humanity sees its place in the cosmos. Galileo Galilei entered the world on February 15th, 1564, in the port city of Pisa, where his father Vincenzo made his living as a lute player and music theorist. The Galilei family was neither wealthy nor particularly poor. They belonged to that comfortable middle class of artisans and scholars who formed the backbone of Renaissance Italian society. Vincenzo was a man of education and curiosity, qualities that he would pass on to his eldest son in ways that would echo through the centuries. From his earliest days, young Galileo displayed the kind of restless intellectual energy that made his tutors both delighted and exhausted. While other children played with wooden toys, Galileo dismantled them to see how they worked. He was fascinated by the mechanics of movement, the way objects fell and rolled and swung. His questions came in endless streams. Why do heavy things fall faster than light things? Why does a pendulum swing in such perfect rhythm? What makes the stars move across the sky each night? His father, recognizing both a gift and a challenge in his son's insatiable curiosity, encouraged these questions even when they disrupted household routines and left the family's furniture in various states of experimental disassembly. Vincenzo understood something profound about learning, that true understanding comes not from memorizing what others have said, but from observing the world directly and asking why things are as they are. The Italy of Galileo's youth was a land caught between worlds. The medieval certainties that had dominated European thought for 1,000 years were beginning to crack, allowing new ideas to sprout like wildflowers through the gaps in ancient stone. This was the High Renaissance, the age of Leonardo da Vinci and Michelangelo, when art and science flowed together like tributaries joining a great river of human creativity. In the universities and workshops of Florence and Pisa, scholars were rediscovering the writings of ancient Greek philosophers and mathematicians. The works of Aristotle, which had been the foundation of European education for centuries, were being read alongside newly translated texts of Archimedes and Euclid. But more importantly, a new spirit was emerging, a willingness to test ancient ideas against direct observation, to trust what one could see and measure, rather than simply accepting what authorities had written. Young Galileo absorbed this intellectual atmosphere like a sponge soaking up summer rain. His education began in the local monastery school, where monks introduced him to Latin, mathematics, and the classical texts that formed the basis of all scholarly learning. But even in these early years, Galileo showed a distinctive approach to knowledge. Where other students memorized and recited, Galileo questioned and experimented. One famous story, possibly apocryphal but revealing nonetheless, tells of young Galileo timing the swings of a bronze lamp hanging in the Cathedral of Pisa. While his classmates fidgeted through long church services, Galileo watched the lamp sway back and forth in the draughts from the high windows, using his pulse to time each swing. He noticed something remarkable. Whether the lamp swung in wide arcs or narrow ones, each complete swing took exactly the same amount of time. This observation of what would later be called the isochronism of the pendulum was just the kind of insight that would characterize Galileo's entire approach to understanding the natural world. Where others saw only a lamp swaying in the breeze, he saw a fundamental principle of motion that could be measured, tested, and understood. At 17, following his father's practical wishes, Galileo enrolled at the University of Pisa to study medicine. The choice made economic sense. Doctors were well paid and respected members of society, and the Galilei family could certainly use the financial security that a medical career would provide. But Galileo's heart was never in the study of human anatomy and traditional remedies. His mind kept drifting to questions of motion, mathematics, and the movements of celestial bodies. The medical curriculum of the late 16th century was still largely based on the ancient texts of Galen and Hippocrates, with little emphasis on direct observation or experimentation. Students were expected to memorize classical authorities rather than examine patients or investigate diseases through systematic study. For a mind like Galileo's, which thrived on questioning and testing, this approach to learning felt like trying to understand music by reading about it, rather than listening to melodies and harmonies. It was during these university years that Galileo first encountered the mathematical works of Euclid, and the experience was nothing short of revelatory. Here was a way of thinking that appealed to everything in his nature, logical, precise, built on clear definitions and step-by-step reasoning that could be tested and verified. Mathematics offered a language for describing the patterns he observed in the natural world, a tool for turning casual observations into precise, quantifiable knowledge. Galileo began spending more time in mathematics lectures than in medical classes, much to the concern of his professors and the frustration of his father. But the young man had found his calling. In the elegant proofs of geometry and the logical structures of arithmetic, he discovered a way of thinking about the world that felt both beautiful and true. His mathematical studies led him to investigate the works of Archimedes, the ancient Greek mathematician and engineer who had used mathematical reasoning to understand everything from the behavior of floating objects to the design of war machines. Archimedes had combined theoretical understanding with practical application in ways that fascinated Galileo. Here was someone who used mathematics not just as an abstract intellectual exercise, but as a tool for understanding how the physical world actually worked. Inspired by Archimedes, Galileo began conducting his own experiments. He built a hydrostatic balance, a precise scale for measuring the density of metals and other materials, based on Archimedean principles. The device was ingenious in its simplicity and remarkable in its accuracy, able to detect differences in density that were invisible to the naked eye. Word of this invention spread through academic circles, bringing the young man his first taste of scientific recognition. But it was Galileo's investigations into the motion of falling objects that truly set him apart from his contemporaries. The accepted wisdom, handed down from Aristotle and taught in every university, held that heavy objects fall faster than light ones. It seemed obviously true. Drop a stone and a feather, and the stone hits the ground first. Aristotle had declared this natural law nearly 2,000 years earlier, and generations of scholars had accepted it without question. Galileo, however, had a different approach to understanding truth. Instead of simply accepting what authorities had written, he decided to test these ideas systematically. According to the stories that have come down to us through the centuries, he began dropping objects of different weights from various heights, carefully observing their motion and timing their falls. What he discovered challenged everything that educated people of his time believed about the nature of motion. When air resistance was minimal, when comparing objects of similar shape at different weights, the objects fell at essentially the same rate. A heavy ball and a light ball dropped simultaneously from the same height, hit the ground at nearly the same moment. This was revolutionary thinking, and it demonstrates something profound about Galileo's approach to knowledge. He was willing to trust his own observations over the written words of ancient authorities, even when those authorities had been respected for centuries. This willingness to question accepted wisdom, to test ideas against direct experience, would become the hallmark of what we now call the scientific method. The young man's experiments with falling objects led him to deeper questions about the nature of motion itself. If heavy objects don't fall faster than light ones, what determines how fast things fall? What forces act on moving objects, and how can those forces be understood mathematically? These questions would occupy him for the rest of his life, leading eventually to insights that would lay the groundwork for Newton's laws of motion. During his university years, Galileo also became fascinated by the mechanical arts, the practical skills of craftsmen, engineers, and instrument makers. While most university scholars looked down on such hands-on work as beneath the dignity of serious intellectual inquiry, Galileo saw it as another path to understanding. He spent time in workshops, learning how gears and pulleys worked, how to grind lenses and calibrate measuring instruments. This combination of mathematical sophistication and practical skill would prove crucial to his later achievements. The telescope that would make him famous was not just a theoretical concept, but a carefully crafted instrument that required precise understanding of optics and meticulous attention to to the details of lens grinding and mounting. Galileo's growing reputation for mathematical insight and experimental innovation led to his first academic appointment in 1589 as professor of mathematics at the University of Pisa. He was just 25 years old, a remarkably young age for such a position, but his unconventional approach to learning had already marked him as someone special. His lectures were unlike anything his students had experienced before. Instead of simply reciting from classical texts, Galileo encouraged his students to think for themselves, to question assumptions, and to test ideas through careful observation and measurement. He demonstrated mathematical principles using physical apparatus, showing how abstract concepts connected to the tangible world of moving objects and mechanical devices. But his teaching methods also created friction with more traditional faculty members. Galileo's willingness to challenge Aristotelian physics wasn't just an academic disagreement. It was seen as a threat to the established order of knowledge. In an age when social and political authority depended partly on intellectual authority, questioning fundamental principles about the nature of the physical world could be seen as questioning authority itself. The tension came to a head when Galileo allegedly conducted his famous experiment from the Leaning Tower of Pisa, dropping objects of different weights from the tower's famous tilted height to demonstrate that they fell at the same rate. Whether this dramatic public demonstration actually occurred is debated by historians, but the story captures something essential about Galileo's character, his willingness to put ideas to public test, even when those tests challenge deeply held beliefs. The experiment, real or legendary, represents a crucial moment in the development of modern scientific thinking. For the first time, someone was systematically using controlled experiments to test fundamental assumptions about how the physical world works. This approach, forming hypotheses, designing tests, and letting observation determine truth, would eventually revolutionize human understanding of everything from the motion of planets to the behavior of atoms. But Galileo's time at Pisa was also marked by frustration. His salary was low, barely enough to support himself, let alone help his family through various financial difficulties. More importantly, his innovative teaching methods and experimental approach had made him enemies among the more conservative faculty. In 1592, when his contract came up for renewal, it was clear that his future at Pisa was uncertain. It was then that an opportunity arose that would change the course of his life and ultimately the history of astronomy. The University of Padua in the Republic of Venice was looking for a new professor of mathematics. Padua was known for its intellectual freedom and tolerance for new ideas, qualities that the Venetian Republic, with its tradition of independence and trade-based prosperity, actively encouraged. The position offered better pay, more academic freedom, and the chance to work in an environment where intellectual curiosity was valued over conformity to traditional authorities. Galileo's reputation had spread beyond Pisa, and his mathematical innovations and experimental approach had attracted attention from scholars throughout Italy. As he prepared to leave Pisa for Padua, Galileo could hardly have imagined where his curiosity would lead him. He was still primarily known as a mathematician and student of motion, someone who asked interesting questions about falling objects and pendulums. The discoveries that would make him famous throughout Europe, the moons of Jupiter, the phases of Venus, the cratered surface of the moon, still lay in the future, waiting for an instrument that had not yet been invented. But the foundation had been laid. The young man who questioned why objects fall as they do, who insisted on testing ideas rather than simply accepting them, who combined mathematical insight with hands-on experimentation, was ready for the next phase of his journey. In Padua, Surrounded by colleagues who valued innovation and free inquiry, Galileo would begin the work that would earn him the title Father of Modern Astronomy. And it was there, in the workshops and lecture halls of that ancient university, that Galileo would encounter the instrument that would open the heavens to human observation, the telescope that would reveal secrets that had been hidden since the dawn of time, waiting for someone curious enough to look up at the night sky and ask not just what was there, but how it all worked. The young man of curiosity was about to become the man who would teach humanity to see the cosmos with new eyes. The year 1609 arrived in Padua like any other, with the gentle warmth of spring awakening the ancient stone buildings and filling the university courtyards with the soft murmur of scholarly conversation. Galileo, now 45 and settled into his professorship, had spent nearly 2 decades teaching mathematics, studying motion, and refining his understanding of the mechanical world. His reputation as an innovative thinker had grown steadily, and his lectures drew students from across Europe who came to learn his unique approach to understanding natural phenomena. But in this particular spring, something extraordinary was stirring in the workshops and markets of Northern Europe. Rumours of a curious new invention that could make distant objects appear close at hand. Dutch lens makers, those patient craftsmen who had spent generations perfecting the art of grinding glass to correct vision, had discovered something remarkable. By arranging certain lenses in a particular sequence, they could create an instrument that magnified far-off objects with startling clarity. The first reports reaching Italy were fragmentary and often contradictory. Some called it a Dutch perspective glass, others referred to it as a spyglass. The stories told of ship captains who could identify vessels on the horizon hours before they reached port, of military commanders who could observe enemy movements from unprecedented distances. But like many rumours in an age when news travelled slowly and often transformed with each telling, the exact nature of this instrument remained tantalizingly unclear. Galileo first heard of this mysterious device through the networks of correspondence that connected scholars across Europe. In an age before scientific journals or rapid communication, knowledge spread through letters between learned individuals, through travellers' tales, and through the informal conversations that took place in university halls and market squares. The descriptions that reached him were intriguing, but frustratingly vague. Something about lenses, something about magnification, something that seemed almost magical in its ability to bring the distant world closer. For most people, such rumours might have remained merely curious gossip, but Galileo's mind worked differently. Where others saw an interesting novelty, he saw possibilities that extended far beyond practical applications for navigation or warfare. His years of studying optics and his hands-on experience with lens grinding had given him insights into how light behaves when it passes through curved glass. If someone had indeed created a device that could magnify distant objects, he wanted to understand exactly how it worked, and more importantly, how it might be improved. The breakthrough came in the summer of 1609, when a Dutch lensmaker arrived in Venice carrying one of these mysterious instruments. Word spread quickly through the scholarly community, and Galileo arranged to examine the device during a brief visit to the city. What he saw was both simpler and more profound than he had expected. A tube containing 2 lenses, one at each end, arranged in a configuration that indeed made distant objects appear larger and clearer. But Galileo's trained eye immediately saw the device's limitations. The magnification was modest, perhaps 3 or 4 times, and the image quality left much to be desired. The view was dim, the field of vision narrow, and there was significant distortion around the edges. For someone who had spent years thinking about optics and the behavior of light, these were not insurmountable problems, but engineering challenges waiting to be solved. Returning to Padua, Galileo set himself the task of not merely copying the Dutch design, but fundamentally improving it. His workshop became a laboratory of experimentation, filled with lenses of different curves and compositions, tubes of various lengths, and the patient tools of the lens grinder's craft. He understood that the key to a superior instrument lay not just in the arrangement of lenses, but in the precision of their manufacture and the careful calculation of their focal properties. The work required a combination of theoretical understanding and practical skill that few people of his era possessed. Galileo had to grind his own lenses, a process that demanded extraordinary patience and precision. Each lens had to be shaped to exact specifications, with curves calculated to bend light in precisely the right way. The glass itself had to be of the highest quality, free from bubbles or imperfections that would distort the image. Night after night, Galileo worked by candlelight, testing different combinations of lenses, experimenting with tube lengths, and gradually refining his understanding of how to optimize the instrument's performance. His mathematical background allowed him to calculate the theoretical relationships between lens curves, focal lengths, and magnification, while his practical experience taught him how to translate those calculations into actual glass and metal. The result of this intensive effort was an instrument far superior to anything that had come before. Where the original Dutch telescopes provided perhaps 3 or 4 times magnification, Galileo's improved design achieved 8, then 10, then eventually 20 times magnification. More importantly, his careful attention to lens quality and alignment produced images that were brighter, clearer, and less distorted than previous versions. Word of Galileo's improved telescope spread quickly through Venice and beyond. The Venetian Senate, recognizing the potential military and commercial advantages of such an instrument, was eager to examine his creation. In a demonstration that would become legendary, Galileo invited the senators to climb the bell tower of St. Mark's Cathedral, where his telescope revealed ships approaching the harbour nearly 2 hours before they were visible to the naked eye. The senators were astounded. In an age when early warning of approaching vessels could mean the difference between successful trade and devastating surprise attack, Galileo's telescope represented a revolutionary advantage. They immediately offered him a permanent position with a substantial salary increase, recognizing that they were witnessing not just a clever novelty, but a transformative technology. But for Galileo, the telescope's most exciting potential lay not in terrestrial applications, but in an entirely different direction. As he refined his instrument and achieved higher magnifications with clearer images, his thoughts turned increasingly toward the night sky. The same device that could reveal distant ships might also reveal secrets of the celestial realm that had remained hidden since the dawn of human civilization. The idea of pointing a telescope at the sky was not immediately obvious to most people of Galileo's era. The heavens were seen as a realm of perfection, populated by objects so distant and unchanging that closer examination seemed unnecessary. The moon appeared smooth and spherical, the planets looked like bright stars, and the Milky Way was merely a faint cloudy band across the night sky. What more could there be to discover? But Galileo's curiosity had never been constrained by conventional assumptions about what was worth investigating. If his telescope could reveal previously hidden details of the terrestrial world, why shouldn't it be able to reveal hidden aspects of the celestial sphere? The same principles of optics that brought distant ships into clear view should work equally well on distant stars and planets. On a clear evening in late 1609, Galileo carried his telescope out into the darkness beyond Padua's city walls, away from the flickering light of torches and candles that might interfere with his observations. The night was crisp and still, with the kind of atmospheric clarity that makes even familiar stars seem to pulse with unusual brilliance. He set up his instrument on a steady support and began the careful process of aligning it with celestial objects. His first target was the moon, that familiar companion that had watched over humanity since the beginning of time. Through the naked eye, the moon appeared as a smooth, luminous disk, marked only by the vague, dark patches that human imagination had long interpreted as the features of a face. The man in the moon of folklore and poetry. But through Galileo's telescope, the moon was transformed into an alien world of startling complexity and beauty. The smooth, perfect sphere of Aristotelian astronomy vanished, replaced by a landscape of mountains, valleys, and vast plains that bore an unmistakable resemblance to the terrain of Earth itself. The lunar surface was rough, cratered, and dramatically three-dimensional, with shadows that shifted and changed as the moon moved through its phases. The implications of this observation were staggering. For nearly 2,000 years, European scholars had accepted Aristotle's teaching that celestial bodies were made of a perfect, unchanging substance utterly different from the corruptible matter of Earth. The moon was supposed to be a flawless crystal sphere, as smooth and unblemished as polished marble. But here, revealed in unprecedented detail, was clear evidence that the moon was a world much like our own, rough, mountainous, and obviously composed of the same kind of matter that makes up terrestrial landscapes. Galileo spent hours sketching what he saw, creating detailed drawings that captured the changing play of light and shadow across the lunar surface. He observed how the shadows moved as the moon's phase changed, allowing him to calculate the height of lunar mountains by analyzing the length of their shadows. Some of these peaks, he determined, were even taller than the highest mountains on Earth. These observations of the moon were revolutionary enough, but they were only the beginning. As Galileo turned his telescope toward other celestial objects, each new view brought revelations that challenged fundamental assumptions about the nature of the cosmos. The planet Venus, which appeared to the naked eye as nothing more than a bright point of light, revealed itself through the telescope to have phases like the moon, sometimes appearing as a thin crescent, sometimes as a gibbous shape, sometimes nearly full. This was extraordinary evidence for the Copernican theory that planets orbit the Sun rather than the Earth. If Venus orbited Earth, as the traditional geocentric model claimed, it could never show the full range of phases that Galileo observed. Jupiter, that wandering star that had puzzled ancient astronomers with its complex motion against the stellar background, proved to have secrets that would overturn everything scholars thought they knew about cosmic architecture. But those discoveries, and their profound implications for humanity's understanding of its place in the universe, would require even more careful observation and months of patient study. The Milky Way, that faint band of light that stretched across the summer sky, dissolved under telescopic scrutiny into countless individual stars, so many stars that their combined light created the cloudy appearance visible to the naked eye. This single observation multiplied the known number of stars by thousands, revealing a universe far vaster and more populous than anyone had imagined. Each night brought new wonders, new challenges to accepted wisdom, new evidence that the cosmos was far stranger and more complex than centuries of scholarship had suggested. Galileo found himself in the extraordinary position of being the first human being to see these cosmic details, the first to witness landscapes and phenomena that had existed since the beginning of time but had remained invisible to every previous generation. The experience was both exhilarating and profoundly humbling. Here was direct evidence that human knowledge of the universe had been woefully incomplete, based on the limited information available to the naked eye, rather than on the full reality that more powerful instruments could reveal. It was as if humanity had been studying the cosmos through a keyhole and had suddenly been given access to a window that revealed the vast complexity beyond. But with these discoveries came responsibility. Galileo recognized that he was witnessing evidence that would fundamentally challenge the accepted understanding of cosmic order. The telescope was not just revealing new details about familiar objects, it was uncovering proof that the basic structure of the universe was different from what everyone believed. As winter approached and the skies grew clearer with the cold, Galileo prepared for a campaign of systematic observation that would document these revolutionary discoveries with the careful precision they deserved. He knew that extraordinary claims would require extraordinary evidence, and that the scholarly world would demand detailed, reproducible observations before accepting such radical departures from traditional astronomy. His workshop filled with notebooks containing sketches, measurements, and careful descriptions of everything he observed. Each night's viewing added new pieces to a cosmic puzzle that was growing ever more complex and wonderful. The man who had once questioned why objects fall as they do was now questioning the very architecture of the heavens themselves. And among all the marvels his telescope revealed, there was one discovery waiting in the darkness around Jupiter that would prove more revolutionary than all the others combined, a discovery that would provide the clearest possible evidence that Earth was not the center of all celestial motion, that other worlds could have moons of their own, and that the universe contained wonders beyond anything human imagination had conceived. The telescope had opened a window to the cosmos, and through that window Galileo was about to glimpse the truth that would change everything. The winter nights of 1610 settled over Padua with unusual clarity, as if the cosmos itself was conspiring to provide perfect conditions for revelation. Galileo had established a routine of observation that began each evening as soon as darkness fell, carrying his telescope to a quiet courtyard where city lights wouldn't interfere with his view of the heavens. The cold made his fingers stiff as he adjusted the instrument's focus, but the crisp air created atmospheric conditions that allowed his improved telescope to perform at its absolute best. On the evening of January 7th, 1610, Galileo turned his attention to Jupiter, that bright wandering star that ancient astronomers had named for the king of the gods. Through his telescope, Jupiter appeared not as a mere point of light, but as a small disk, clearly planetary in nature. But what caught his attention that night was something far more extraordinary than the planet's size or brightness. There were 3 small stars arranged in a perfectly straight line near Jupiter, 2 to the east and 1 to the west. This was curious enough to warrant careful note-taking, but Galileo had observed many stellar configurations that proved unremarkable upon further study. What made this observation different was his growing habit of returning to interesting objects night after night, tracking any changes that might occur. The next evening he pointed his telescope toward Jupiter again, expecting to see the same arrangement of stars. But the configuration had changed. All 3 small stars were now positioned to the west of Jupiter, still in a straight line, but in an entirely different arrangement from the night before. This was puzzling. Stars were supposed to be fixed in their positions relative to each other, moving only as part of the great celestial sphere that rotated around the Earth each day. Yet these 3 points of light had clearly moved relative to Jupiter in just 24 hours. Galileo's scientific training told him to observe more carefully before drawing any conclusions. Perhaps clouds had obscured his view the previous night, or maybe he had made an error in his initial observations. But as night followed night, the pattern became unmistakable. These were not stars at all, but objects that orbited around Jupiter, just as the Moon orbits around Earth. On January 10th, he observed only 2 of the objects, leading him to wonder if Jupiter itself might be obscuring the third. By January 11th, all 3 were visible again, but in yet another configuration. On January 13th, he discovered a 4th such object, bringing the total to 4 small bodies that danced around Jupiter in what was clearly a miniature solar system. The implications of this discovery were staggering beyond anything Galileo had imagined when he first turned his telescope skyward. For nearly 2,000 years, one of the strongest arguments against the idea that Earth might orbit the Sun had been the problem of the Moon. If Earth moved through space, critics asked, how could the Moon possibly keep up? Wouldn't our planet leave its satellite behind as it travelled through its orbit? But here, circling Jupiter, were 4 moons that clearly accompanied their planet as it moved through the heavens. These Medicean stars, as Galileo diplomatically named them in honour of his potential patron Cosimo de' Medici, proved definitively that celestial bodies could indeed orbit one object, while that object orbited something else. The Moon could easily accompany Earth in its orbit around the Sun, just as these 4 moons accompanied Jupiter. Night after night, Galileo tracked the movements of Jupiter's satellites, recording their positions and noting the patterns of their orbital dance. Sometimes one or more would disappear entirely, passing behind Jupiter or in front of it, casting tiny shadows on the planet's surface or being eclipsed by the planet's shadow. These phenomena provided additional evidence that these were indeed solid bodies, orbiting in space, not mere optical illusions or atmospheric effects. The mathematical precision of their movements fascinated him. Each moon followed its own orbital period, the innermost completing its circuit around Jupiter in just over a day and a half, while the outermost took more than 2 weeks. The regularity of these motions suggested that the same mathematical laws that govern planetary motion might apply to these smaller celestial bodies as well. But beyond their scientific significance, Jupiter's moons represented something profound about the nature of cosmic order itself. Earth was not unique in having a satellite. Other worlds had moons of their own, creating complex hierarchies of orbital motion that suggested a universe far more intricate and wonderful than previous generations had imagined. As Galileo continued his observations through the winter and spring of 1610, he also refined his studies of other celestial objects. His observations of Venus became increasingly detailed and systematically recorded. The planet's phases, which he had first noticed the previous autumn, followed a predictable pattern that provided some of the strongest evidence yet discovered for the Copernican model of the solar system. When Venus appeared as a thin crescent, it was large and bright, indicating that it was relatively close to Earth. When it showed a full phase, it appeared smaller and dimmer, suggesting it was farther away. This pattern made perfect sense if Venus orbited the Sun. When the planet was on the same side of the Sun as Earth, it would appear large and crescent-shaped like a new moon. When it was on the opposite side of the Sun from Earth, it would appear smaller and fully illuminated. The traditional geocentric model in which Venus orbited Earth could not explain these observations. If Venus circled our planet, it should always appear as a crescent, never showing the gibbous and full phases that Galileo's telescope clearly revealed. Here was observational proof that at least one planet orbited the Sun rather than the Earth. His continued studies of the Moon revealed ever more details about our nearest celestial neighbour. Galileo observed that the boundary between light and shadow on the lunar surface, what astronomers call the terminator, was not smooth but jagged and irregular, exactly what would be expected if the Moon's surface were mountainous and rough. He watched the tips of lunar mountains catch the first rays of sunlight appearing as isolated bright points beyond the main terminator line, just as high peaks on Earth are illuminated before the surrounding valleys during sunrise. These observations allowed him to calculate the heights of lunar mountains with remarkable accuracy. By measuring the distances of these isolated bright spots from the main terminator and applying basic trigonometry, he determined that some lunar peaks rose to heights of 4 miles or more above the surrounding terrain, higher than any mountain known on Earth at that time. The level of detail visible through his telescope continued to amaze him. He could observe the changing patterns of light and shadow as the lunar day progressed, watching familiar features appear and disappear as the sun's angle changed. The moon revealed itself to be a complex three-dimensional world with a geography as varied and interesting as that of Earth itself. Galileo's observations of the stars through his telescope yielded discoveries that were perhaps even more revolutionary in their implications. Stars that appeared single to the naked eye often resolved into multiple star systems when viewed through his instrument. The constellation Orion, familiar to observers since ancient times, revealed far more stars than anyone had suspected. Some of them arranged in patterns that suggested an underlying structure invisible to unaided vision. But it was his observations of the Milky Way that most dramatically expanded human understanding of the scale of the universe. That faint band of light stretching across the night sky, which poets had described as a celestial river or pathway for the gods, dissolved under telescopic scrutiny into countless individual stars. So many stars, in fact, that they defied easy counting. Thousands upon thousands of distant suns, each presumably similar to our own sun but so far away that their combined light appeared as a continuous glow to the naked eye. This single observation multiplied the known population of the universe by an almost incomprehensible factor. If the Milky Way contained thousands of stars, and if each star might be similar to our sun, then the cosmos was far vaster and more populous than anyone had imagined. The philosophical implications were staggering. If the universe contained thousands of suns, might it not also contain thousands of worlds like Earth? Saturn, that most distant of the planets known to ancient astronomers, presented Galileo with a puzzle that his telescope could reveal, but not quite resolve. The planet appeared to have some kind of appendages or attachments on either side, giving it an oddly elongated appearance that didn't match the circular shape of other planets. Galileo described Saturn as appearing triple, with a central body flanked by 2 smaller objects. What he was actually observing were Saturn's rings, but his telescope lacked the resolution to clearly distinguish them as separate structures. The rings appeared as vague protrusions that seemed to change shape and size over time, sometimes appearing prominent and sometimes nearly disappearing altogether. This mystery would not be solved until later astronomers developed more powerful telescopes, but Galileo's observations established that even the most distant planets held surprises waiting to be discovered. Throughout 1610, as news of Galileo's discoveries spread across Europe, the scholarly world responded with a mixture of excitement, skepticism, and alarm. Some astronomers, given access to telescopes of their own, confirmed his observations and added discoveries of their own. Others, lacking good instruments or the skill to use them effectively, questioned whether the telescopic images were real or merely artifacts created by the lenses themselves. The theological implications of these discoveries were even more challenging than the scientific ones. If the moon was a world like Earth, rough and mountainous rather than a perfect crystalline sphere, what did this say about the supposed perfection of the heavens? If other planets had moons of their own, what made Earth special in the cosmic scheme? If the universe contained thousands of previously unknown stars, how did this affect humanity's understanding of its place in creation? Galileo approached these questions with characteristic care, focusing on the observational facts rather than their broader philosophical implications. His role, as he saw it, was to report what his telescope revealed, not to resolve the theological debates that might arise from those discoveries. He was a mathematician and natural philosopher, not a theologian, and he preferred to let others wrestle with the larger questions while he continued his systematic exploration of the cosmos. But he was also acutely aware that his discoveries represented more than mere academic curiosities. The evidence he was accumulating supported the Copernican model of the solar system, which placed the Sun rather than the Earth at the centre of planetary motion. This was not just a technical disagreement among astronomers. It challenged fundamental assumptions about humanity's place in the cosmic order that had shaped religious and philosophical thought for centuries. The moons of Jupiter proved that Earth was not the only centre of celestial motion. The phases of Venus demonstrated that at least one planet orbited the Sun. The rough, mountainous surface of the Moon showed that celestial bodies were made of the same kinds of material as Earth. The countless stars revealed by telescopic observation suggested a universe far larger and more complex than traditional cosmology had imagined. Each of these discoveries, considered individually, might have been absorbed into existing frameworks of understanding, with minor modifications, but taken together, they painted a picture of cosmic reality that was fundamentally different from what scholars had believed for nearly 2 millennia. The universe was revealing itself to be stranger, vaster, and more wonderful than human imagination had conceived. As 1610 drew to a close, Galileo prepared to publish his findings in a work that would bring his discoveries to the attention of scholars throughout Europe. He knew that extraordinary claims would require extraordinary evidence, and he had spent months carefully documenting his observations with the precision and detail that such revolutionary discoveries demanded. The book he was preparing, Sidereus Nuncius, or Starry Messenger, would announce to the world that the cosmos was far different from what everyone had believed. It would describe landscapes on the Moon, satellites orbiting Jupiter, and countless stars invisible to the naked eye. It would present observational evidence that challenged the basic assumptions of traditional astronomy and philosophy. But Galileo also understood that publishing such discoveries would inevitably lead to controversy. The implications of his telescopic observations extended far beyond astronomy, into realms of theology and philosophy where he had no desire to venture. Yet the evidence was undeniable, and the pursuit of truth demanded that these discoveries be shared with the scholarly world, regardless of the debates they might provoke. As he put the finishing touches on his manuscript, Galileo could hardly have imagined the storms of controversy that lay ahead. The telescope had revealed wonders beyond his wildest expectations, but it had also opened questions that would prove far more difficult to resolve than the technical challenges of lens grinding and celestial observation. The man who had sought to understand the heavens through careful observation was about to discover that some truths, no matter how carefully documented, would not be welcomed by those whose worldview they challenged. In the quiet of his study during the early months of 1610, Galileo faced a challenge unlike any he had encountered in his decades of scholarly work. Before him lay pages covered with sketches, measurements, and careful descriptions of celestial phenomena that no human being had ever witnessed before. The question was not whether these observations were accurate. He had checked and rechecked them countless times. But how to present discoveries so extraordinary that they would inevitably be met with skepticism, disbelief, and possibly accusations of fraud or delusion. The manuscript that would become Sidereus Nuncius, the Starry Messenger, required a delicate balance between scientific precision and diplomatic presentation. Galileo understood that he was not merely reporting new astronomical data, but announcing a fundamental revision of humanity's understanding of the cosmos. Such claims demanded not only meticulous documentation, but also careful consideration of how they would be received by the scholarly and religious authorities of his time. He began the work with characteristic attention to detail, describing his improvements to the telescope and the methods he used to ensure accurate observations. This technical introduction served multiple purposes. It established his credentials as a skilled instrument maker, provided enough detail for others to replicate his telescope, and demonstrated that his discoveries were not the result of optical illusions or inferior equipment. The description of lunar observations came first, accompanied by detailed drawings that showed the moon's surface with unprecedented clarity. Galileo's artistic skills, honed through years of studying perspective and proportion, allowed him to create illustrations that captured not just the positions of lunar features, but their three-dimensional quality. The shadows and highlights in his drawings made it impossible to mistake the moon for a smooth sphere. Here was clear visual evidence of a world with mountains, valleys, and plains, much like those on Earth. But it was his account of Jupiter's satellites that would prove most revolutionary. Galileo presented his discovery methodically, describing night after night of observations that track the movements of these Medicean stars with mathematical precision. He included tables showing their positions relative to Jupiter over time, demonstrating the regularity of their orbital motions and leaving no doubt that these were genuine celestial bodies rather than optical artifacts. The diplomatic naming of Jupiter's moons after the Medici family was a calculated decision that served both scientific and practical purposes. By honouring Cosimo de' Medici, the Grand Duke of Tuscany, Galileo hoped to secure patronage that would allow him to continue his research without the financial pressures that had long constrained his work. But the gesture also served to present his discoveries in a context that emphasized their magnificence rather than their controversial implications. Galileo completed the manuscript in just 2 months, working with an urgency driven partly by excitement and partly by the knowledge that others were beginning to construct telescopes of their own. Priority in scientific discovery mattered greatly in an age when reputation and patronage often depended on being first to announce important findings. He arranged for the book to be printed in Venice, where the Republic's tradition of intellectual freedom offered some protection from potential censorship. Sidereus Nuncius was published in March 1610, and the response was immediate and dramatic. The initial printing of 550 copies sold out within days, an extraordinary success for a technical work on astronomy. Word of Galileo's discoveries spread through the networks of correspondence that connected scholars across Europe, creating a sensation that extended far beyond academic circles. Johannes Kepler, the brilliant German astronomer who had spent years developing his laws of planetary motion, was among the first to respond publicly to Galileo's claims. His initial reaction mixed excitement with caution. The discoveries, if true, provided strong support for the Copernican model of the solar system that both men favoured, but they were so extraordinary that verification was essential before accepting them fully. Kepler's endorsement carried enormous weight in the scholarly community. His reputation for mathematical rigour and careful analysis meant that his support lent credibility to Galileo's observations. When Kepler finally gained access to a telescope of sufficient quality to confirm the existence of Jupiter's moons for himself, His enthusiastic confirmation helped establish the reality of Galileo's discoveries beyond reasonable doubt. But not all responses were positive. Some astronomers, lacking access to good telescopes or the skill to use them effectively, questioned whether the images Galileo described were real or merely artifacts created by the lenses themselves. The telescope was such a new invention that many scholars were genuinely uncertain about its reliability. Could an instrument that magnified distant objects be trusted to show them accurately, or might it create false images that looked convincing but corresponded to nothing in reality? This skepticism was not entirely unreasonable. Early telescopes were difficult instruments to use effectively, requiring steady hands, good eyesight, and considerable practice to achieve clear views. Many of the telescopes hastily constructed by other instrument makers were of poor quality, producing dim, distorted images that bore little resemblance to what Galileo's carefully crafted instruments revealed. Scholars who attempted to verify his observations with inferior equipment often saw nothing that matched his descriptions. The challenge of telescope construction became a crucial factor in how Galileo's discoveries were received. Creating a good telescope required not just theoretical knowledge of optics, but practical skills in lens grinding that few people possessed. The quality of available glass varied greatly, and even small imperfections in lens shape or alignment could render an instrument nearly useless for astronomical observation. Some critics went further, suggesting that the telescope's images might be supernatural in origin or the result of demonic deception. In an age when the boundary between natural philosophy and magic was not always clear, some religious authorities worried that instruments capable of revealing previously hidden aspects of creation might be trespassing into realms that God had chosen to keep concealed from human observation. Galileo responded to such criticisms with characteristic patience and precision. He invited skeptics to examine his instruments and observe the phenomena for themselves, confident that direct experience would overcome theoretical objections. He also began sending telescopes to prominent astronomers and nobles across Europe, ensuring that those with the most influence in scholarly circles would have access to instruments capable of confirming his discoveries. The process of verification was gradual but ultimately convincing. As more astronomers gained access to good telescopes and developed the skills necessary to use them effectively, confirmation of Galileo's observations accumulated. The moons of Jupiter proved to be particularly compelling evidence. Their regular orbital motions could be predicted and tracked, making it impossible to dismiss them as optical illusions or atmospheric effects. The Tuscan court of Cosimo de' Medici proved receptive to Galileo's diplomatic overtures. The Grand Duke was pleased to have the celestial discoveries associated with his family name, and he recognized the prestige that came with patronizing such groundbreaking research. In July 1610, Galileo accepted a position as chief mathematician and philosopher to the Grand Duke, a title that freed him from teaching duties and provided the financial security necessary for continued research. This appointment marked a crucial transition in Galileo's career. No longer bound by the constraints of university life, he could devote himself entirely to observation and research. The move from Padua to Florence also brought him closer to Rome, where the implications of his discoveries would eventually be debated by the highest authorities of the Catholic Church. News of the telescopic discoveries reached Rome quickly, where they were received with a mixture of fascination and concern. Some Jesuit astronomers, particularly those at the Collegio Romano, were intrigued by the possibilities that telescopic observation offered for advancing astronomical knowledge. The Jesuit order had a strong tradition of mathematical and scientific scholarship, and many of its members were well equipped to understand the technical aspects of Galileo's work. But the theological implications of the discoveries could not be ignored. If the moon was a world like Earth, rough and imperfect rather than crystalline and pure, what did this say about the supposed perfection of the heavens? If other planets had moons of their own, how did this affect traditional understanding of Earth's unique place in creation? These questions required careful theological analysis, not just astronomical verification. The scholarly community's response to Siderius Nuncius also reflected broader tensions about the nature of knowledge and authority. For centuries, European learning had been based primarily on the study of classical texts, with direct observation of nature playing a secondary role. Galileo's approach, trusting careful observation over ancient authorities, represented a fundamental shift in how knowledge could be acquired and validated. Some scholars embraced this new empirical approach, recognizing that it offered unprecedented opportunities for advancing human understanding of the natural world. Others worried that abandoning traditional authorities would lead to chaos and uncertainty, undermining the stable foundations of learning that had guided European scholarship for generations. The debate over telescopic astronomy became part of a larger conversation about the proper relationship between observation, reason, and authority in the pursuit of knowledge. This conversation would continue long after Galileo's specific discoveries had been accepted, shaping the development of what would eventually be called the scientific method. Meanwhile, telescope making became a rapidly developing craft as demand for the instrument spread across Europe. Lens grinders in various cities attempted to replicate and improve upon Galileo's designs, leading to a gradual improvement in the quality and availability of telescopes. This technological diffusion was crucial for the eventual acceptance of telescopic astronomy. As more people gained access to good instruments, the discoveries became reproducible rather than dependent on Galileo's unique skills. The success of Siderius Nuncius also established Galileo's reputation beyond the specialized world of academic astronomy. His clear, accessible writing style made complex astronomical concepts understandable to educated readers who lacked technical training, helping to create a broader public interest in telescopic discoveries. This popular appeal would prove both beneficial and problematic, as his work attracted attention from authorities who might otherwise have ignored purely technical astronomical debates. By the end of 1610, Galileo found himself in an unprecedented position. He was famous throughout Europe for discoveries that had fundamentally altered humanity's understanding of the cosmos. He enjoyed the patronage of powerful nobles and the respect of leading scholars. His telescopes were sought after by astronomers and princes alike, and his continuing observations promised even more revolutionary discoveries. But fame and success also brought new responsibilities and dangers. The man who had once been free to pursue knowledge for its own sake now found his work scrutinized by authorities, with interests that extended far beyond scientific understanding. The telescope had revealed wonders in the heavens, but it had also opened questions about truth, authority, and the proper limits of human inquiry that would prove far more difficult to resolve than the technical challenges of celestial observation. As Galileo prepared for the next phase of his astronomical career, he could hardly have imagined the storms of controversy that lay ahead. The evidence he had gathered supported the Copernican model of the solar system, but presenting that evidence publicly would require him to navigate treacherous waters where science, theology, and politics intersected in ways that few scholars had ever encountered. The starry messenger had delivered his news to the world, but the world's response would prove more complex and challenging than any celestial phenomenon he had yet observed. The success of Siderius Nuncius brought Galileo not only fame and patronage, but also the kind of attention that extends far beyond the usually quiet realm of academic astronomy. By 1611, his telescopic discoveries were being discussed, not just in university halls and noble courts, but in the corridors of ecclesiastical power, where questions of cosmic order intersected with matters of divine authority and biblical interpretation. The Catholic Church's initial response to Galileo's discoveries was more nuanced than later events would suggest. Many church officials, particularly the Jesuit astronomers at the Collegio Romano in Rome, approached the telescopic observations with genuine scientific curiosity. These were scholars who understood mathematics and astronomy, men capable of appreciating both the technical achievement of the improved telescope and the significance of what it revealed about celestial mechanics. When Galileo visited Rome in 1611, he was received with considerable honour. Cardinal Robert Bellarmine, one of the Church's most respected theologians and a man known for his intellectual rigour, arranged for the Jesuit astronomers to verify Galileo's observations using their own instruments. After careful study, they confirmed the existence of Jupiter's moons, the phases of Venus, and the rough surface of the Moon. The reality of these phenomena was no longer in doubt. But confirmation of the observations did not resolve the deeper questions they raised. The problem was not whether Galileo had seen what he claimed to see, but what these discoveries meant for humanity's understanding of cosmic order and divine design. The moons of Jupiter and the phases of Venus provided strong evidence for the Copernican model of the solar system, which placed the Sun rather than the Earth at the centre of planetary motion. This was where astronomy began to intersect with theology in ways that made church authorities increasingly uncomfortable. The geocentric model, which placed Earth at the centre of the universe, was not merely a scientific theory, but a framework that seemed to align with certain passages in Scripture and with traditional understanding of humanity's special place in creation. If Earth was just another planet orbiting the Sun, what did this say about the biblical account of creation or humanity's unique relationship with God? The tension was not immediately explosive. During Galileo's 1611 visit to Rome, he was honoured by Pope Paul V and celebrated by cardinals and scholars who appreciated his contributions to natural philosophy. Cardinal Maffeo Barberini, who would later become Pope Urban VIII, was particularly impressed by Galileo's work and seemed genuinely interested in the philosophical implications of telescopic astronomy. But beneath the surface courtesy, more conservative voices within the church hierarchy were growing concerned. The Copernican model had been around for nearly 70 years since the publication of Copernicus's De Revolutionibus, but it had remained largely a mathematical hypothesis used to improve astronomical calculations. Galileo's observations provided physical evidence that this hypothesis might actually describe reality, transforming what had been a useful computational tool into a potentially revolutionary worldview. The controversy deepened as Galileo began to argue more explicitly for the Copernican system. His observations of Venus had shown conclusively that this planet orbited the Sun, not the Earth. The moons of Jupiter demonstrated that not all celestial bodies revolved around our planet. The rough, mountainous surface of the Moon suggested that celestial bodies were made of the same kind of matter as Earth, challenging traditional distinctions between the perfect heavens and the corruptible terrestrial realm. In letters and conversations, Galileo began to present these discoveries as evidence for a heliocentric universe. He argued that the telescope had revealed the true structure of the cosmos, and that this structure supported the mathematical model proposed by Copernicus. This was a significant step beyond merely reporting observations. It was advocating for a specific interpretation of what those observations meant. The response from church authorities became increasingly cautious. In 1615, Cardinal Bellarmine wrote a letter clarifying the Church's position on Copernicanism. While not condemning the theory outright, he distinguished between treating it as a useful mathematical hypothesis and accepting it as a description of physical reality. The Church could tolerate Copernican astronomy as a computational tool, but it was not prepared to endorse the idea that the Earth actually moved through space. This distinction reflected a sophisticated understanding of the relationship between mathematical models and physical reality. Many astronomical theories throughout history had been useful for prediction, without necessarily describing how the universe actually worked. The complex system of epicycles used in Ptolemaic astronomy, for example, could predict planetary positions quite accurately, even though few astronomers believed that planets literally travelled in the intricate circular patterns the mathematics required. But Galileo's discoveries had moved the debate beyond abstract mathematical modelling. The telescopic evidence suggested that at least some aspects of the Copernican model corresponded to physical reality. Venus really did orbit the Sun, not the Earth. Jupiter really did have moons that accompanied it as it moved through the heavens. These were not merely computational conveniences, but descriptions of actual celestial mechanics. The theological implications became more acute as Galileo began to address questions of biblical interpretation. Critics of Copernicanism often cited scriptural passages that seemed to describe a stationary Earth and a moving sun. Joshua commanding the sun to stand still, for example, or the psalmist declaring that God set the earth on its foundations so that it should never be moved. Galileo's response to these biblical arguments was both thoughtful and dangerous. In his letter to the Grand Duchess Christina, written in 1615, he argued that scripture and natural philosophy operated in different domains. The Bible, he suggested, was intended to teach spiritual truths about salvation and morality, not to provide technical information about astronomical mechanics. When biblical language seemed to conflict with scientific observation, it should be understood as accommodation to common ways of speaking, rather than as precise description of physical processes. This approach to biblical interpretation was not necessarily heretical. Many church fathers had made similar distinctions between spiritual and literal meanings in Scripture. But coming from a layman who was simultaneously advocating for a controversial astronomical theory, such arguments appeared presumptuous to church authorities. Galileo seemed to be suggesting that he could determine which parts of Scripture should be taken literally, and which should be understood metaphorically, based on his astronomical observations. The situation was further complicated by the broader religious context of the early 17th century. The Catholic Church was still responding to the Protestant Reformation, which had challenged papal authority and traditional biblical interpretation. In this environment, anything that seemed to undermine scriptural authority or suggest that individual scholars could reinterpret biblical passages was particularly sensitive. The Counter-Reformation had emphasized the Church's exclusive authority to interpret Scripture, partly as a response to Protestant claims that individuals could understand biblical truth through personal study. Galileo's arguments about accommodation and metaphorical interpretation, however well-intentioned, appeared to challenge this ecclesiastical authority by suggesting that astronomical observation could guide biblical interpretation. By 1616, the controversy had escalated to the point where formal action became necessary. The Congregation of the Index, responsible for determining which books posed threats to Catholic doctrine, was asked to evaluate the status of Copernican astronomy. After deliberation, they declared that the proposition that the sun stands still at the centre of the universe was foolish and absurd in philosophy, and formally heretical since it explicitly contradicts the sense of many passages of sacred scripture. The proposition that the Earth moves was condemned as deserving of the same censure in philosophy, and at least erroneous in faith. Copernicus's De Revolutionibus was placed on the index of forbidden books until corrected, meaning that it could not be read without modifications that treated the heliocentric model as purely hypothetical. Cardinal Bellarmine met privately with Galileo to inform him of this decision and to instruct him not to hold, teach, or defend the Copernican theory. The exact details of this meeting would later become crucial, as different accounts emerged of whether Galileo was given a formal injunction that completely prohibited him from discussing Copernicanism, or merely advised to avoid advocating it as physical truth. Galileo's response to this setback was characteristically diplomatic. He accepted the Church's decision publicly and promised to comply with its restrictions, but privately he continued to believe that his telescopic observations provided compelling evidence for the Copernican model, and he began looking for ways to present this evidence without explicitly violating the prohibitions placed upon him. The 1616 decree did not end Galileo's astronomical career, but it fundamentally changed the context in which he worked. He could no longer openly advocate for Copernican astronomy, but he could continue making observations and reporting discoveries that might indirectly support heliocentric theory. This created a delicate balancing act between scientific integrity and ecclesiastical obedience that would define the rest of his career. For several years after 1616, Galileo focused his public work on less controversial topics. He studied the behavior of floating bodies, investigated the strength of materials, and continued his telescopic observations of comets and other celestial phenomena. But the fundamental tension between his scientific convictions and the Church's theological concerns remained unresolved. The situation changed dramatically in 1623 when Cardinal Maffeo Barberini was elected Pope Urban VIII. Barberini had long been an admirer of Galileo's work and had even written a poem celebrating his astronomical discoveries. The new pope was known for his intellectual sophistication and his appreciation for learning and the arts. Many of Galileo's supporters hoped that Urban VIII might prove more receptive to Copernican astronomy than his predecessors had been. Galileo was encouraged by his friends to request permission to write about the competing theories of cosmic structure, presenting the arguments for both geocentric and heliocentric models in a balanced way that would educate readers without explicitly advocating for either position. This seemed like a reasonable compromise that would allow for scholarly discussion while respecting the Church's concerns about premature acceptance of unproven theories. Urban VIII agreed to this proposal, giving Galileo permission to write about the two chief world systems as long as he treated the Copernican model as a mathematical hypothesis rather than as established fact. The Pope reportedly insisted that any such work should conclude with the observation that God, in his omnipotence, could have created the universe in ways that human reason might not be able to fully comprehend. This papal permission seemed to offer a path forward that would satisfy both Galileo's desire to present his evidence and the Church's need to maintain theological authority. The stage was set for what Galileo hoped would be his masterwork, a comprehensive comparison of geocentric and heliocentric astronomy that would allow readers to evaluate the evidence for themselves. But as Galileo began work on this new book, the delicate balance between scientific argument and theological sensitivity would prove far more difficult to maintain than anyone had anticipated. The dialogue concerning the two chief world systems would become the work that transformed a scholarly disagreement into a personal conflict that would define the rest of Galileo's life. The man who had discovered new worlds in the heavens was about to learn that some boundaries are more dangerous to cross than the vast distances between planets. In 1633, at the age of 69, Galileo found himself confined to his villa at Arcetri, in the hills overlooking Florence. The small estate, surrounded by olive groves and vineyards, offered views across the Tuscan landscape that had inspired generations of artists and poets. Here, in this peaceful setting, the man who had revolutionized humanity's understanding of the cosmos would spend his remaining years pursuing the work that had always driven him, the patient observation and mathematical description of the natural world. The restrictions placed upon him were significant but not total. He could not travel freely, could not publish works on astronomy without special permission, and was required to recite penitential psalms as prescribed by his sentence. But within these constraints, Galileo discovered something that many might find surprising, a kind of freedom that came from turning his attention to questions that had long fascinated him but had been overshadowed by the drama of cosmic architecture. His villa became a laboratory, where the principles he had developed for studying celestial motion could be applied to understanding the mechanics of earthly phenomena. The same mathematical approach that had revealed the patterns in planetary orbits could illuminate the behavior of falling bodies, the strength of materials, and the laws that governed motion on every scale, from the swing of a pendulum to the trajectory of projectiles. During these years, Galileo completed what many scholars consider his greatest work. Discourses and mathematical demonstrations relating to two new sciences, commonly known as the two new sciences. This book, written in the form of dialogues between three characters, discussing problems in physics and engineering, represented the culmination of a lifetime of thinking about motion, force, and the mathematical principles underlying physical phenomena. The work was remarkable for several reasons, not least of which was how Galileo managed to write and publish it, despite the restrictions placed upon him. Since he could not openly publish in Catholic territories, the manuscript was smuggled to Protestant Holland, where it was printed by the Elsevier publishing house in 1638. This international publication network allowed Galileo's ideas to reach scholars throughout Europe, ensuring that his contributions to natural philosophy would not be suppressed by local authorities. But more importantly, the two new sciences demonstrated that Galileo's approach to understanding nature, careful observation combined with mathematical analysis, could be applied far beyond astronomy. The book laid the foundation for what would become the science of mechanics, establishing principles that would later be developed by Newton into a comprehensive theory of motion and force. In the peaceful hours of his confinement, Galileo returned to questions that had intrigued him since his student days at Pisa. Why do objects fall as they do? What determines the strength of materials? How can the motion of projectiles be predicted mathematically? These investigations required no telescope, no observation of distant planets, no engagement with controversial theories about cosmic structure. They demanded only careful experimentation, precise measurement, and the kind of mathematical reasoning that had always been Galileo's greatest strength. His studies of falling bodies, begun decades earlier with experiments allegedly conducted from the Leaning Tower of Pisa, reached their mature form during these years. Galileo developed a mathematical description of uniformly accelerated motion that accurately predicted how objects would behave when dropped or thrown. This work required extraordinary precision, as the differences he was measuring occurred over fractions of seconds and distances of inches or feet. The experimental techniques he developed were ingenious in their simplicity. To study the acceleration of falling bodies, He used inclined planes that slowed the motion enough to be measured accurately with the timekeeping devices available to him. By rolling balls down ramps of different angles and carefully timing their motion, he could study the same physical principles that governed free fall, but in a controlled way that allowed for precise measurement. These experiments revealed mathematical relationships that had profound implications for understanding motion throughout the universe. The same principles that governed a ball rolling down a ramp in his villa also described the motion of projectiles through the air and, ultimately, the orbital motion of planets around the Sun. The universality of physical laws, the idea that the same mathematical principles apply to motion on Earth and in the heavens, was one of Galileo's most important insights. His work on the strength of materials grew out of practical questions that had long interested engineers and architects. Why do larger structures require proportionally thicker supports? What determines how much weight a beam can carry before breaking? These questions had obvious applications for construction and engineering, but Galileo approached them with the same mathematical rigor he had applied to celestial mechanics. The results were groundbreaking. Galileo discovered that the strength of materials does not scale linearly with size, a finding that explained why very large animals must have proportionally thicker bones than smaller ones, and why the largest possible trees are limited by the strength of wood. These insights into scaling relationships would later prove crucial for engineering projects of all kinds, from bridges and buildings to ships and machines. During these years at Arcetri, Galileo also received visits from students and colleagues who came to learn from the master of mathematical natural philosophy. Among these visitors was Evangelista Torricelli, a brilliant young mathematician who would later become famous for his work on atmospheric pressure and the invention of the barometer. These conversations allowed Galileo to share his insights with a new generation of scholars who would carry his methods and discoveries forward. The relationship between teacher and students during this period reveals something beautiful about the transmission of knowledge. Despite the restrictions placed upon him, Galileo continued to inspire and educate young minds who were eager to understand the mathematical principles underlying natural phenomena. His villa became an informal academy, where the new experimental philosophy could be discussed and developed. Galileo's correspondence during these years shows a man who remained intellectually vigorous and curious despite advancing age and physical limitations. His eyesight, damaged by decades of telescopic observations and detailed experimental work, gradually failed, but his mind remained sharp and his interest in natural philosophy undiminished. He continued to think about problems in mechanics, to propose new experiments, and to refine his understanding of the mathematical principles governing motion. One of the most touching aspects of this period was Galileo's relationship with his daughter, Sister Maria Celeste, a nun at the nearby convent of San Matteo. Their correspondence reveals a deep bond between father and daughter, sustained by shared intellectual interests and genuine affection. Sister Maria Celeste often helped with copying manuscripts and managing correspondence, becoming an essential partner in her father's continued scholarly work. The peaceful routine of villa life allowed Galileo to engage with natural philosophy in a more contemplative way than had been possible during the busier years of his career. Without the pressures of teaching, court obligations, or public controversy, he could pursue lines of inquiry simply because they interested him, exploring questions that had no immediate practical application, but offered insights into the fundamental nature of physical reality. His investigations during this period often had a playful quality that reflected both his advanced age and his freedom from external pressures. He studied the behavior of pendulums, not because they had immediate applications, but because their regular motion revealed mathematical relationships that were beautiful in their simplicity. He analysed the flight of projectiles not for military purposes, but because the parabolic curves they traced through space demonstrated the geometric elegance underlying natural processes. This playful approach to investigation was characteristic of Galileo throughout his career, but it became more pronounced during his years at Starry. Freed from the need to justify his work in terms of practical applications or theoretical debates, he could pursue knowledge for its own sake, driven by the same curiosity that had motivated him as a young student, timing the swings of lamps in Pisa Cathedral. The publication of the two new sciences in 1638 demonstrated that confinement had not diminished Galileo's creativity or his ability to contribute to human understanding. The book was immediately recognized as a masterwork of scientific reasoning, presenting fundamental insights into the nature of motion and force that would influence natural philosophy for centuries to come. European scholars who read the work were struck by its combination of practical relevance and theoretical sophistication. Here were mathematical principles that could be used to solve real problems in engineering and construction, but which also revealed deep truths about the underlying order of the physical world. The book showed that the same experimental and mathematical methods Galileo had used to revolutionize astronomy could be equally powerful when applied to terrestrial phenomena. By the late 1630s, Galileo's reputation among scholars throughout Europe had, if anything, grown stronger during his years of confinement. His methods of investigation were being adopted by natural philosophers across the continent, and his discoveries were being extended and refined by a new generation of mathematicians and experimenters. The restrictions placed upon him had not prevented the spread of his ideas, but had perhaps enhanced their influence by creating an aura of martyrdom around his scientific work. The correspondence he received from admirers across Europe showed how his approach to natural philosophy was inspiring others to pursue similar investigations. Students of his methods were discovering new mathematical relationships in fields ranging from optics to mechanics, applying the combination of careful observation and mathematical analysis that had become his signature approach to understanding nature. As the 1630s drew to a close, Galileo could look back on a life that had fundamentally changed how humans understand their place in the cosmos and their ability to comprehend the natural world through reason and observation. His telescopic discoveries had revealed the true structure of the solar system. His mathematical investigations had laid the foundation for modern physics, and his experimental methods had demonstrated the power of careful observation combined with mathematical reasoning. The villa at Starry had become more than a place of confinement. It had become a laboratory where the principles of modern science were refined and perfected. In the quiet hills overlooking Florence, surrounded by the timeless beauty of the Tuscan landscape, Galileo had found a different kind of freedom, the freedom to pursue pure knowledge, to ask questions simply because they were interesting, and to trust that careful observation and mathematical reasoning could reveal truths about the natural world. As his strength began to fail in the early 1640s, Galileo could take satisfaction in knowing that his life's work had opened pathways to understanding that future generations would follow and expand. The methods he had developed, the discoveries he had made, and the principles he had established would outlive any temporary restrictions on their dissemination. The man who had taught humanity to see the cosmos with new eyes had also taught them how to discover truth through the patient application of reason to the evidence of the senses, a gift that would prove more enduring than any single astronomical discovery. When Galileo died on January 8, 1642, in his villa at Starry, The ripples of his discoveries had already spread far beyond the hills of Tuscany, beyond the universities of Europe, and into the very foundations of how humanity understood its relationship with the cosmos. His telescopic observations had revealed new worlds, but more importantly, his methods of investigation had created new ways of discovering truth about the natural world that would guide scientific inquiry for centuries to come. The immediate legacy of Galileo's astronomical work can be traced through the generation of scholars who built directly upon his discoveries. Johannes Kepler, working with the precise observational data compiled by Tycho Brahe, had already demonstrated that planetary orbits were elliptical rather than circular, refining the Copernican model that Galileo's observations had supported. But it was Galileo's proof that other worlds could have satellites of their own, those 4 moons dancing around Jupiter, that provided the conceptual breakthrough needed to understand how complex orbital systems could work. Within decades of Galileo's death, astronomers across Europe were using increasingly sophisticated telescopes to discover more satellites around the known planets. Giovanni Cassini, working at the Paris Observatory, discovered 4 moons of Saturn between 1671 and 1684, proving that Jupiter was not unique in having a family of satellite worlds. These discoveries followed naturally from Galileo's demonstration that the cosmos was far more complex and varied than anyone had previously imagined. The methodological legacy of Galileo's work proved even more important than his specific discoveries. He had demonstrated that careful observation, precise measurement, and mathematical analysis could reveal truths about the universe that were not accessible through pure reasoning or reliance on ancient authorities. This empirical approach to natural philosophy, what we now call the scientific method, became the foundation for all subsequent progress in astronomy and physics. Isaac Newton, born the year Galileo died, grew up in a world where the combination of observation and mathematics had already proven its power to unlock cosmic secrets. When Newton formulated his law of universal gravitation in the 1680s, he was building directly on foundations that Galileo had laid. The idea that the same mathematical principles could describe both terrestrial and celestial motion, that an apple falling from a tree and the moon orbiting Earth followed the same physical laws, was a natural extension of insights that had emerged from Galileo's work. Newton's Principia Mathematica, published in 1687, represented the mathematical culmination of the revolution that Galileo had begun with his telescope. The universal laws of motion and gravitation that Newton derived could explain not only the elliptical orbits that Kepler had discovered, but also the precise movements of Jupiter's moons that Galileo had first observed. The cosmos revealed itself to be a vast clockwork mechanism, operating according to mathematical principles that human reason could discover and understand. But Galileo's influence extended beyond the specific mathematical formulations of celestial mechanics. He had fundamentally changed how scientists approach the investigation of nature. Before Galileo, natural philosophy was largely based on logical reasoning from first principles, often derived from the works of ancient authorities like Aristotle. Galileo demonstrated that nature itself, carefully observed and measured, was a more reliable guide to truth than any human authority, no matter how respected. This shift from authority-based to evidence-based reasoning transformed not just astronomy but all of natural philosophy. The generation of scientists who followed Galileo, Robert Hooke, Christian Huygens, Antony van Leeuwenhoek, and many others, applied his empirical methods to fields ranging from microscopy to mechanics, from optics to biology. Each brought the same commitment to careful observation and mathematical analysis that had characterized Galileo's approach to understanding the heavens. The telescopic revolution that Galileo initiated continued to accelerate throughout the 17th and 18th centuries. Each improvement in telescope design revealed new details about familiar objects and entirely new categories of celestial phenomena. William Herschel's discovery of Uranus in 1781 doubled the known size of the solar system and demonstrated that even basic facts about cosmic architecture were still being uncovered. Herschel's systematic surveys of the night sky, conducted with telescopes far more powerful than anything Galileo could have imagined, revealed that the universe contained not just more stars than previously known, but entirely different types of celestial objects. Nebulae, cloudy patches of light that appeared stellar to smaller telescopes, resolved into vast collections of stars, suggesting that the Milky Way itself might be just one of many such systems scattered throughout space. These discoveries followed the pattern that Galileo had established. Each improvement in observational capability revealed that the universe was larger, more complex, and more wonderful than previous generations had imagined. The method of discovery, building better instruments, making more precise observations, and applying mathematical analysis to understand what those observations revealed, remained fundamentally the same approach that Galileo had pioneered. The philosophical implications of Galileo's legacy proved as lasting as its scientific applications. He had demonstrated that human beings, through careful observation and reasoning, could understand fundamental truths about the cosmos. This was a profoundly optimistic view of human intellectual capability, suggesting that the universe was comprehensible to minds willing to set aside preconceptions and follow the evidence wherever it led. This confidence in human reason, combined with respect for empirical evidence, became one of the defining characteristics of what historians call the scientific revolution and the Enlightenment. The idea that natural phenomena could be understood through observation and mathematical analysis, rather than through appeal to traditional authorities, spread from astronomy and physics into fields like chemistry, biology, and eventually even social and political thought. The precision instruments that Galileo had used to measure the positions and movements of Jupiter's moons established a tradition of exact measurement that became central to all subsequent scientific work. The development of increasingly sophisticated measuring devices, more accurate clocks, more precise telescopes, more sensitive balances, allowed scientists to detect smaller and smaller effects, leading to discoveries that would have been impossible without this commitment to quantitative precision. By the 19th century, this tradition of precise measurement had led to discoveries that revealed new layers of cosmic complexity. The tiny wobbles in stellar positions, measurable only with the most sophisticated instruments, provided the first evidence that other stars had planets of their own. The minute shifts in spectral lines revealed that stars and nebulae were moving toward or away from Earth at enormous speeds, eventually leading to the discovery that the universe itself was expanding. These discoveries required not just better instruments but also the mathematical sophistication to interpret what the instruments revealed. The statistical analysis of stellar positions, the mathematical modelling of planetary perturbations, the theoretical physics needed to understand how matter behaves under extreme conditions. All of these developments built on the foundation that Galileo had established by demonstrating that mathematical reasoning could unlock cosmic secrets. The democratization of astronomical knowledge that began with Galileo's clear, accessible writing continued to influence how scientific discoveries were communicated to broader audiences. His decision to write in Italian rather than Latin, to use dialogues rather than formal treatises, and to focus on observable phenomena rather than abstract theory, established a tradition of making scientific knowledge accessible to educated readers beyond the narrow circle of professional scholars. This tradition of public scientific education became increasingly important as astronomical discoveries revealed the true scale and age of the universe. When 19th century astronomers demonstrated that stars were so distant that their light took years to reach Earth, and when 20th century cosmologists showed that the universe was billions of years old, these discoveries challenged traditional views of humanity's place in creation just as profoundly as Galileo's discoveries had challenged the geocentric cosmos. The ability to communicate complex scientific ideas to non-specialist audiences, pioneered by Galileo, became essential for helping society understand and adapt to revolutionary, new knowledge about the nature of reality. The same clear reasoning and careful attention to evidence that characterized Galileo's scientific work also characterized his efforts to explain these discoveries to readers who lacked specialized mathematical training. The space age of the 20th century represented the ultimate vindication of Galileo's vision that other worlds were genuine places that could, in principle, be visited and explored. When the first spacecraft flew past Venus and Mars, they revealed worlds that were strange and alien but undeniably real. Planets with their own weather systems, geological histories, and complex physical environments. The exploration of Jupiter's moons by robotic spacecraft in the late 20th and early 21st centuries provided details about these worlds that Galileo could never have imagined. Europa's subsurface ocean, Io's volcanic activity, Ganymede's magnetic field. Each discovery revealed that the small points of light Galileo had observed through his telescope were complex worlds with their own unique characteristics and histories. Modern astronomy's discovery of thousands of planets orbiting other stars has confirmed that planetary systems are common throughout the galaxy, exactly as Galileo's observations had suggested they might be. Each new exoplanet discovery demonstrates that the cosmos contains a vast diversity of worlds, some similar to planets in our solar system, and others unlike anything we had previously imagined. The search for life beyond Earth, one of the most active areas of contemporary astronomical research, follows directly from questions that Galileo's discoveries first raised. If other stars have planets, and if those planets might have conditions suitable for life, then the cosmos might be populated with forms of life that evolved independently from terrestrial biology. This possibility, which would have seemed pure fantasy before telescopic astronomy, now represents a serious scientific question addressed through careful observation and analysis. The mathematical modelling techniques that modern astronomers use to understand everything from stellar evolution to galaxy formation represent sophisticated extensions of the basic approach that Galileo pioneered, using mathematical reasoning to interpret observational data and predict the behaviour of physical systems. Whether modelling the formation of planetary systems around young stars or predicting the merger of distant galaxies, contemporary astronomers follow the same fundamental methodology that Galileo established. Perhaps most importantly, Galileo's legacy includes the understanding that scientific knowledge is always provisional and subject to revision based on new evidence. His willingness to abandon traditional beliefs when they conflicted with careful observations established a precedent for the self-correcting nature of scientific knowledge that remains central to how science operates today. As we look toward the future of astronomical discovery, with space telescopes capable of detecting potentially habitable planets around nearby stars, with gravitational wave detectors opening entirely new windows on cosmic phenomena, with sophisticated computer simulations revealing how galaxies and planetary systems form and evolve, we are following paths that lead back to a hillside villa in Tuscany, where an aging scholar taught humanity to trust what careful observation reveals about the cosmos. The man who first saw mountains on the moon and moons around Jupiter had demonstrated something profound about human capability, that patient observation, careful reasoning, and mathematical analysis could reveal truths about the universe that no previous generation had access to. This optimistic faith in human ability to understand the cosmos continues to drive astronomical research today, 4 centuries after Galileo first pointed his telescope toward the stars. Every new discovery, from the most distant galaxies to the smallest asteroids, represents another step along the path that Galileo first opened when he dared to look up at the night sky and trust what his improved vision revealed. And so we come to the end of our gentle journey through the life of Galileo Galilei, a journey that began in the olive groves of Renaissance Tuscany and led us through the most profound transformation in human understanding since our ancestors first looked up at the stars and wondered what they were seeing. Perhaps you've drifted peacefully through some of these chapters, carried along by the rhythm of discovery and contemplation. If so, that's perfectly wonderful. But if you're still here with me in these quiet hours, still following this story of curiosity and courage, take a moment to appreciate the remarkable life we've explored together. Tonight, when you look up at the moon, whether it's a thin crescent barely visible in the twilight, or a full moon casting silver shadows across your room, you're seeing it as Galileo taught humanity to see it, not as a smooth, perfect sphere of celestial crystal, but as a world with mountains and valleys, plains and craters, a landscape as complex and fascinating as our own Earth. Every time someone notices the rough terminator line between lunar light and shadow, every time a child points a small telescope toward our nearest neighbour and gasps at the detail visible there, they're participating in the same sense of wonder that filled Galileo on those winter nights in 1609. The 4 bright stars that seem to line up near Jupiter when you observe it through binoculars or a small telescope, those are still called the Galilean satellites, still dancing in the same orbital patterns that amazed their discoverer over 4 centuries ago. Io, Europa, Ganymede and Callisto continue their celestial waltz, sometimes hiding behind their giant planet, sometimes casting tiny shadows on its banded surface, sometimes lined up like jewels on an invisible string stretching across space. Modern spacecraft have revealed these moons to be worlds of extraordinary diversity and beauty. Europa's ice-covered ocean might harbour life in its dark depths. Io's volcanic surface is the most geologically active place in the solar system. Ganymede generates its own magnetic field. Callisto bears the scars of 4 billion years of cosmic bombardment. Each of these worlds has proven to be far stranger and more wonderful than Galileo could have imagined when he first saw them as tiny points of light through his handmade telescope. But in a deeper sense, every detail that modern astronomy has revealed about these distant worlds confirms the fundamental insight that Galileo's observations first suggested. The cosmos is filled with real places, each with its own character and history, each following the same physical laws that govern motion and matter throughout the universe. The method he pioneered, careful observation combined with mathematical reasoning, continues to unlock secrets about worlds so distant that their light takes millions of years to reach our telescopes. Why do we call Galileo the father of modern astronomy? Not simply because he made important discoveries, though he certainly did that. Not just because he improved the telescope, though that technological achievement opened new realms of cosmic exploration. We honour him with this title because he fundamentally changed how humans approach the investigation of nature itself. Before Galileo, studying the heavens meant reading ancient texts, reasoning from first principles, and accepting the authority of respected scholars. Galileo demonstrated that the cosmos itself, carefully observed and mathematically analysed, was a more reliable teacher than any human authority. He showed that nature keeps accurate records of its own behaviour, written in the language of motion and force, light and shadow, position and time, and that human beings, through patient observation and careful reasoning, could learn to read that cosmic script. This transformation in how we seek knowledge about the universe represents perhaps Galileo's most lasting gift to humanity. Every modern astronomical discovery, from the detection of gravitational waves to the imaging of black holes, follows the same fundamental approach that Galileo pioneered. Trust what careful observation reveals, use mathematics to understand the patterns in natural phenomena, and remain open to discoveries that challenge our preconceptions about how the universe works. The space telescopes currently orbiting Earth, Hubble, James Webb and others, are the direct descendants of that first crude instrument that Galileo assembled in his workshop in Padua. When these sophisticated observatories reveal galaxies that formed when the universe was young, or detect the atmospheric composition of planets orbiting distant stars, they're extending a line of investigation that began when Galileo first pointed his telescope toward Jupiter and noticed those 4 small stars that seem to move from night to night. The search for life beyond Earth, one of the most compelling questions in contemporary science, grows directly from insights that Galileo's discoveries first made possible. If other stars have planets, and if those planets might have conditions suitable for life, then we might not be alone in the cosmos. This possibility, which would have seemed pure fantasy before telescopic astronomy revealed the true nature of our solar system, now drives billion-dollar space missions and represents one of the most active areas of astronomical research. But perhaps most remarkably, Galileo's legacy includes something that transcends any specific scientific discovery: the understanding that the universe is comprehensible to human reason, the same intellectual capabilities that allow us to understand music and poetry, to design buildings and solve mathematical problems, also allow us to understand how stars shine, how planets form, and how galaxies evolve across cosmic time. This is a profoundly optimistic view of human nature and cosmic order. It suggests that we are not strangers in an alien universe, but participants in a cosmic story that we can learn to understand through careful observation and thoughtful analysis. The atoms in our bodies were forged in the hearts of ancient stars. The mathematical relationships that govern the motion of planets also describe the behavior of electrons in our brains. We are quite literally made of star stuff, thinking about stars. When you rest tonight under the same sky that Galileo studied, you're connected not just to his individual story, but to the entire human endeavour of trying to understand our place in the cosmos. Every question a child asks about why the moon changes shape, every amateur astronomer who sets up a telescope in their backyard, every professional researcher analysing data from distant galaxies, all of them are following paths that lead back to that hillside villa in Tuscany, where an aging scholar demonstrated that careful observation could reveal cosmic truths. The wonder that fills us when we contemplate the vastness of space, the intricate beauty of planetary rings, or the delicate dance of binary stars is the same wonder that motivated Galileo to spend night after night mapping the movements of Jupiter's moons. The curiosity that drives modern astronomers to search for Earth-like planets around nearby stars is the same curiosity that led a young professor in Pisa to question why objects fall as they do. In this long view of cosmic time and human understanding, individual lives might seem brief and small, but there's another way to think about our place in this story. You are part of an unbroken chain of consciousness that stretches from the first humans who looked up at the stars in wonder to the astronomers of the far future who will witness the sun's evolution into a red giant. The capacity for wonder and understanding that allows you to appreciate Galileo's discoveries is the same capacity that allowed him to make them in the first place. The methods that Galileo developed for understanding the cosmos, careful observation, precise measurement, mathematical analysis, willingness to question accepted authorities, have proven to be among humanity's most powerful tools for discovering truth about the natural world. These methods have revealed not just the structure of our solar system, but the age and scale of the universe, the evolution of stars and galaxies, and the fundamental forces that govern all matter and energy. Yet for all the sophistication of modern astronomy, the basic human experience of looking up at the night sky and feeling a sense of wonder and connection remains unchanged. The same stars that inspired ancient poets and guided early navigators still shine down on us tonight. The same moon that Galileo studied through his telescope still rises in our evening sky, still pulls at our oceans with the same gravitational force that has shaped Earth's tides for billions of years. When modern astronomers discover a new exoplanet orbiting a distant star, when they detect ripples in space-time from the collision of black holes, when they peer deeper into space and further back in time than any previous generation could imagine, they are participating in the same grand human project that Galileo helped establish, the patient, careful investigation of cosmic reality through observation and reason. Tonight, as you prepare to rest under this ancient sky, you might take a moment to appreciate the extraordinary journey that humanity has taken from Galileo's time to our own. We have learned that our galaxy contains hundreds of billions of stars, that the observable universe contains hundreds of billions of galaxies, that the cosmos is nearly 14 billion years old and still expanding from the moment of its birth. We have sent robotic explorers to every planet in our solar system and beyond. We have landed on comets, orbited asteroids, and detected planets around stars so distant that their light left them before human civilization began. We have learned that the universe is stranger and more wonderful than anyone in Galileo's time could have imagined, filled with neutron stars and black holes, dark matter and dark energy, phenomena that challenge our understanding and inspire new questions. But at the heart of all these discoveries lies the same basic insight that Galileo demonstrated over 4 centuries ago. The universe follows laws that human reason can discover and understand. The cosmos is not arbitrary or capricious, but ordered and logical, operating according to principles that patient investigation can reveal. As you drift towards sleep tonight, perhaps with moonlight filtering through your window or starlight, barely visible beyond the glow of human-made illumination, you're resting under the same cosmic dome that has sheltered every human who has ever lived. The stars above you tonight are the same stars that shone on Galileo as he worked in his garden at Arcetri, the same stars that will shine on future generations who will make discoveries we cannot yet imagine. In this vast continuity of cosmic time and human wonder, your individual life is both infinitesimally brief and profoundly significant. You are the universe becoming aware of itself, if only for a moment. Your capacity to appreciate the beauty of Saturn's rings, to feel awe at the scale of cosmic distances, to find peace in the regular motion of planets and stars. This capacity makes you a participant in the same cosmic story that Galileo helped humanity learn to read. The telescope that Galileo built opened a window between Earth and the cosmos, a window that has grown wider and clearer with each passing generation. Tonight, that window remains open. The same curiosity that drove a young man in Renaissance Italy to question why objects fall as they do, to build better instruments for seeing distant things, to trust his observations over ancient authorities, continues to drive human exploration of the cosmos. Sweet dreams, fellow travellers through space and time. The stars keep watch over us all, as they have since consciousness first stirred in the universe and began to wonder about itself. In the morning, when the stars fade into the brightness of day, they will still be there, still following the same laws that Galileo helped us understand, still waiting for the next generation of curious minds to discover new secrets hidden in their ancient light. Thank you for joining me on this peaceful exploration of Galileo's extraordinary life and lasting legacy. Until we meet again under starlit skies, may your rest be deep, your dreams be filled with wonder, and your connection to the cosmos bring you the same sense of peace and awe that motivated the father of modern astronomy to spend his life reaching toward the stars. Clear skies and gentle starlight, the sleepy astronomer,